Welcome to this online training, an introduction to the Platform Designer system design tool. My name is Steve. This training is available for desktop viewing as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. In this training, we will cover two main topics: an introduction to the Platform Designer tool itself and an introduction to the Platform Designer interconnect. By the end of this training, you will be able to describe the benefits and advantages of using Platform Designer to build an embedded system design in an Intel FPGA, and you will be able to describe the structure and flow of data through the interconnect. Let's start by discussing the Platform Designer tool itself. System design can be a difficult process. Here's an example of a typical system. Different devices or IP in your system, referred to as components in Platform Designer, may have different interfaces that need to communicate with each other in order for the system to work. This requires a lot of engineering effort to design custom interface or glue logic to enable this communication, including things like arbitration and width matching. This type of logic does not add a lot of value to your design, but it is necessary to get the system connected. Putting this together is a naturally error-prone process, as the designer must resolve the various data, control, and status signals between the different interfaces, as well as the timing of these signals. Platform Designer is the solution to these system design problems. It provides a single interface for building simple to complex system designs inside your target FPGA device. It features an easy-to-use graphical interface that lets you build the system quickly and automatically generate the interconnect required to connect the components together. When you use Platform Designer to design your system, the tool automatically generates a custom-built interconnect structure that facilitates communication between all your system components. This abstracts away from the designer the manual process of manipulating interfaces and individual signals, and allows you to instead focus on integrating your value-add system blocks, thereby increasing your productivity. There are many benefits to building a system with Platform Designer. Platform Designer simplifies complex system design by raising the level of abstraction during system development. Instead of designing at the signal level, Platform Designer allows you to work at the system component level. Along with this, Platform Designer provides a standard platform for integrating available IP and your own custom logic. It enables design reuse by allowing you to create custom IP components that can be reused in any other system design. The tool also scales easily for larger designs by using a hierarchical approach to system design. The end result is a reduced time to market, made possible by reducing overall development, reducing the number of errors when connecting the system together, and simplifying the verification process. Platform Designer includes many features that make it the perfect tool for creating any type of system design. The system interconnect automatically generated by the tool is a high-performance interconnect modeled after networking protocols, allowing for high-speed packetized data transfer between components. As mentioned, Platform Designer supports hierarchical system design, allowing any system to be used and reused as part of any other Platform Designer system. Platform Designer supports industry-standard interfaces, allowing designers to easily connect to and support various standardized systems and data configurations. Finally, Platform Designer offers enhanced capabilities for IP management, allowing designers to package individual components or entire systems as IP for distribution to other users. Platform Designer makes complicated system design easy by focusing on the integration of IP using a custom and dynamically generated system interconnect fabric. The tool outputs HDL files that define the interconnect between components and are then compiled in the standard Intel Quartus Prime software design flow. The tool provides a simple-to-use wizard for creating your own custom IP components that can be reused in any Platform Designer system design. You can distribute your custom components to others or store them in an IP repository. For verification, Platform Designer simplifies the process of full system or individual component simulation through the use of bus functional models, or BFMs. A BFM is a special golden reference component that can be controlled from a test bench during a simulation using a provided API. The API and scripts generated by Platform Designer work in standard simulation tools such as the Intel-provided QuestaSim HDL simulator and other third-party simulation tools. For runtime hardware debug, you can perform interactive data transfers and control the system design through graphical toolkits using System Console. Finally, Platform Designer is very easy to use. The tool is mostly GUI-based, but you can completely script the process of building and generating a system. The main user interface of Platform Designer that allows for simple system design is basically a list. You create a list of components you want in your system and then connect the components together. To do this, you add components from the IP catalog, similar to the IP catalog found in the main Intel Quartus Prime software. The IP catalog in Platform Designer lets you easily find, select, and add individual IP components as well as entire system designs to the current system. Existing systems added to a new system are referred to as subsystems, highlighting the hierarchical design capabilities of the tool. Once you've added components to the system, the Connections panel lets you quickly connect IP component interfaces and subsystems together. Through these simple GUI elements and push-button HDL code generation, Platform Designer automates the usual error-prone integration tasks, allowing you to easily build systems at a higher level of abstraction than if you manually wrote the code yourself. So what designs can be built with Platform Designer? Well, pretty much any FPGA design can take advantage of Platform Designer in some way. If we look at the breakdown of typical designs, we can divide the parts of these designs into two main types, a control plane and a data plane. The control plane uses memory-mapped interfaces where host components access addressable memory locations or control and status registers via read and write commands. The data plane uses point-to-point interfaces where packetized data continuously moves or streams through the system. The data plane uses switching mechanisms like multiplexers and demultiplexers or data manipulators like aggregators or bridges to control the flow of the data. As such, Platform Designer target applications can include video and image processing, high-speed interfaces and protocols, as well as embedded and memory applications. No matter what your application, you can use Platform Designer to build it. So, don't system design tools like Platform Designer create embedded systems? And don't embedded systems require a processor for control? What if a design doesn't necessarily need a processor? Platform Designer systems and processors, like the Intel Neo soft processor, are not synonymous. A Platform Designer system only requires components that have the ability to initiate transfers or requests, and components to receive those transfers or requests. The controlling components don't even need to be inside the system itself. They can be in another part of the Intel Quartus Prime project or even off-chip. But to implement a control mechanism for the control plane, a host such as a state machine or a DMA can be used to initiate requests to agent components. For the data plane, a source such as a video camera or pattern generator can initiate transfers. You can, of course, still use processors like the Intel Neos processor or the ARM Cortex hard processors found in SoC devices, but this is not required for using Platform Designer. However, Platform Designer is required for implementing these processors in a design. Now that you understand a bit about what Platform Designer is and what it can do, let's take a look at the interconnect generated by the tool and how it is built to support any type of system design. The Platform Designer interconnect is dynamically generated when the system is manually or automatically generated in the tool. It is based on the component parameter settings and component connections made in the Platform Designer user interface. Again, the idea is to let the user focus on what is connected to the system, not how the components are connected together. As such, the Platform Designer interconnect architecture is modeled after networking architectures and protocols, so it is optimized for performance, using a packet-based data transfer strategy for components to communicate. The interconnect is made up of four main structures: standard interfaces, the Platform Designer packet, network-on-chip routing resources, and embedded system structures. The first key part of the Platform Designer interconnect architecture is the use of standard interfaces. Standard interfaces are what components use to communicate with each other and how they connect to the interconnect. Platform Designer supports multiple standard interface variants organized into two general categories: Avalon, a standard created and supported by Intel specifically for building system designs in FPGA devices, and the ARM AMBA AXI standard, used by ARM throughout their processor IP, including the ARM Cortex processors found in Intel FPGA SoC devices. Starting with Avalon, the Avalon memory-mapped standard interface is an easy-to-use little-endian interface primarily used for control plane applications. With this interface, data transfers occur when host interfaces initiate read and write requests to the system, and Avalon agent interfaces respond to those requests. The Avalon streaming interface standard is big-endian and used primarily for data plane applications. In these types of systems, data is transferred while being manipulated by logic structures like filters, transforms, or other processing algorithms. With this standard, source interfaces stream data into the system to a dedicated target, and sink interfaces receive data from a dedicated source in the system. Connections are always point-to-point, but one-to-many streams can be implemented using streaming muxes and demuxes. Data transfers occur either through a simple handshaking mechanism between the source and sink, or a credit-based variant has the sink define exactly when and how many transfers it can accept from the source. The second category of standard interfaces is the ARM AMBA AXI standard and its many variants. This standard is supported by Platform Designer and works in a similar fashion to the Avalon standard interfaces. However, the ARM standards include a number of additional features used by ARM processors and IP, including enhanced security and many more options for DMA data transfers. These standard interfaces work well for either control or data planes. While ARM AMBA 3 AXI and ARM AMBA 4 AXI interfaces are the most commonly used, the ARM AMBA 4 AXI Lite interface is a simpler version that has a more limited feature set but utilizes fewer signals, making its implementation simpler. The ARM AMBA 4 AXI ST standard is a streaming standard, similar to Avalon streaming. Note, however, that connections between these two different streaming standards are not allowed. So what's the big deal with requiring the use of standard interfaces? There are several advantages to using standard interfaces in system design. First, with a standard interface, required signals and those signals' behavior is defined by the standard. Thus, you don't have to worry about manually defining, assigning, and wiring up control, status, and data signals. This results in a reduction in errors that could occur if this was done incorrectly. With a standard interface, the communication between system components is predefined by the interface. This means that two components that support that interface can communicate with one another with minimal effort. It also means that components that support different interfaces can still communicate with each other by means of bridges and adapters. Bridges and adapters map the individual control, status, and data signals between the interfaces of the components. This lets you design at a higher level because you only have to worry about connecting components and systems together, and not about the individual signals that make up a component's interface. Making changes to a design becomes much quicker and easier. Finally, with standard interfaces, verification can be performed on a component by comparing its behavior against the standard. This simplifies the verification process by letting you use verification tools like bus functional models and interface compliance assertions and monitors. As mentioned, standard interface use in Platform Designer supports interoperability through bridges and adapters in the interconnect. With Platform Designer, your system can be all Avalon interfaces or all ARM AMBA AXI interfaces, but this is not required. You can have a mix of supported interface types, and Platform Designer will manage the communication between them. In the example shown here, an Avalon host and an ARM AMBA AXI manager communicate with an Avalon agent and an ARM AMBA AXI subordinate through the Platform Designer interconnect. With the Platform Designer interconnect between them, any host or manager device or interface can communicate with any agent or subordinate device or interface. So the designer only has to add the components to the system and connect them together to begin performing data transfers. The interconnect is automatically generated in such a way to handle any mismatches or differences between the two sides of the transfer. Platform Designer packets are used by the interconnect to move requests and data through the system. All memory map transactions are converted into Platform Designer command and response packets. The size of the packet is not explicitly defined. This allows Platform Designer to set the size of the packet based on the components added to the system in order to minimize the resources needed to construct the interconnect. For example, if a system uses all 32-bit components, the data field of the packet would be 32 bits. If a 16-bit component is connected to the 32-bit component, a width adapter is automatically added and the packet data is handled appropriately. This packetizing mechanism is what allows different standard interface types to be connected together. As long as an interface's transfer request gets converted into this packet correctly, it can be converted into a request for another interface type at the receiving end. There may be some concern that, when using a packetized network interconnect, a system may experience increased latency. This concern is a non-issue for two reasons. One, the packet format used by Platform Designer is wide enough that a complete transaction can be contained in a single packet. This means that write requests can be completed within one cycle, and that read requests can be completed in as little as one cycle each direction. While this minimizes latency, it can make it more difficult to meet timing and performance requirements. As such, pipeline stages can be added to the interconnect either automatically or manually by the designer. The second reason that latency is not a concern is that the command and response packets use different paths. Since they do not have to compete for the same network resources, system throughput is increased. This table shows an example of a Platform Designer packet. Packetization allows for future changes to the fields while maintaining backwards compatibility, so the table may not exactly reflect the format in a particular version of Platform Designer. The fields in white are used by all packet types. The fields in green are used when ARM AMBA AXI interface requests or responses are moved through the interconnect. They are ignored or removed when converting to Avalon interfaces. Some packet fields to highlight include the address field, which stores the byte address of the lowest data byte in the packet, the transaction type field, which stores the type of transaction being performed, whether it's a read, write, or posted transaction, and the data field, which stores the data to be written in a write command packet or the data that was read in a read response packet. The source ID field holds the ID of the originator of the packet, while the destination ID holds the ID of the packet target. Here are the rest of the packet fields. The byte count field contains the total number of bytes in the transfer, while the burst wrap field specifies the wrapping behavior for packets that burst across the packet boundary. The response field is unique to ARM AMBA AXI interfaces and includes the response signal status, required for all transactions on the interface. The thread ID field supports the ability to perform different transactions on the same interface for multiple threads of data. The QoS and data sideband fields are unique to the ARM AMBA 4 AXI standard as well. Note that even though the Avalon specification does not currently make use of all of the features of the ARM AMBA AXI standard, support for some features may be added in future updates. The third important aspect of the Platform Designer System Interconnect is the Network on Chip, or NoC architecture. The NoC serves to transfer packets of data through the system as quickly and directly as possible to facilitate communication. It is built and customized automatically based on the options and connections made in the tool. For memory-mapped interfaces, read and write transfers are converted into the wide packet format just discussed and sent through the system on a command network from host or manager to agent or subordinate, where they are converted back into memory-mapped transfer requests. Avalon streaming interfaces are implemented in the transport layer of the architecture to simplify the packet transfer. Responses from agents or subordinates are again converted into packets and sent through the system back to the requesting host or manager on a separate response network, where they are again converted back into memory-mapped transfer responses. Separate command and response networks increase the concurrency of multiple simultaneous data transfers. For streaming transfers, not shown here, the data is already packetized as part of the interface standard itself, so those packets are transferred through the system as is on their own separate point-to-point streaming connections. The final aspect of the interconnect implementation is the use of embedded system structures for handling memory addressing, and data multiplexing and arbitration for routing commands and responses to their proper destinations. These structures facilitate the communication between the multiple host and agent interfaces that make up a system. Translation and adaptation logic structures packetize data to and from the supported standard interfaces and handles any differences between the two sides of the transfer, such as different data bus widths or mismatched burst sizes. With memory addressing, each agent interface is assigned an address in a host interface's addressable memory space. A host communicates with that agent by issuing read and write transfer requests to that agent's address. Platform Designer automatically generates decoding logic to make this happen. With data multiplexing, Platform Designer automatically creates muxes on the inputs of host interfaces so they can receive responses from multiple agents. Thus, a host can issue transfer requests with multiple agents, and the interconnect automatically handles the return of data from the agents back to the host by controlling these data muxes. Finally, with arbitration, Platform Designer automatically creates logic for agent interfaces so they can communicate with multiple connected hosts. The arbiter controls which host has access to the agent at any one time. The selection of which host has priority for accessing a particular agent and how long they have that access can be controlled in the system. When it comes to host and agent interfaces, Platform Designer supports simultaneous multiple host parallel access. This allows multiple hosts to transfer data simultaneously. Unlike traditional host-side arbitration architectures, in which each host must wait until it is granted access to the shared bus, multiple memory-mapped host interfaces can simultaneously perform transfers with independent agents. Arbitration logic stalls a host only when multiple hosts attempt to access the same agent during the same cycle. Basically, the tool creates multiple mini interconnects to isolate independent data transfers. This feature enables a significant bandwidth improvement at the expense of additional resource usage by the interconnect. With this feature, you can make trade-offs when building the system between when and where it is used to provide balance, for example, by grouping devices in the system based on their bandwidth requirements. High bandwidth devices can have their own connections, while others can share the same connection point. The physical connection between a host and an agent only exists if it is specified in the Platform Designer user interface. If the connection is not specified, Platform Designer does not waste logic resources to provide a connection between the two interfaces. This concludes the training. To summarize, you should now see that Platform Designer is a design tool that provides you with a powerful platform for building FPGA-based systems, from the simple to the very complex. Using Platform Designer allows you as the designer to focus on the actual IP in your system and not worry about the logic needed for your IP components to communicate with each other. Finally, once a system is constructed, Platform Designer builds a custom, high-performance interconnect structure that enables communication between all the connected components in your system. To learn more about Platform Designer, see the standard or pro version of the Platform Designer user guide found with all the other Intel Quartus Prime software user guides at the link shown here. For more information about the standard interfaces supported by Platform Designer, see the Avalon and ARM-AMBA AXI interface specifications. Also, don't forget about the built-in help found in both the Intel Quartus Prime software and Platform Designer. Free self-paced e-learning is available as well. Check out the 2-part basic training about how to build a Platform Designer system design, as well as the 4-part series of advanced Platform Designer topics. You can learn details about the standard interfaces supported in Platform Designer and about the unique features found only when using Platform Designer in the Intel Quartus Prime Pro Edition. We also offer a free 1-day instructor-led virtual training class that goes into detail on Platform Designer use and includes a complete lab exercise where you get the chance to build and test a system design on an Intel FPGA development kit. Intel offers many options for learning about our FPGA products and for training on their use. The Intel FPGA YouTube channel contains a number of 5-minute quick videos, along with longer, more in-depth training. The Intel FPGA training website is the place to go to learn about our recommended curriculum for every type of user and to register for a class. While there, you can register for over 300 e-learning courses, just like this one, made up of narrated slides presented in an interactive player. You can also register for one of our full-day instructor-led training classes taught by experienced training engineers, either in person or virtually over the web. All instructor-led courses have hands-on lab exercises to practice the concepts you learn. If you need further assistance, Intel FPGA provides many self-help resources. Check out the landing pages accessed from the main Intel website that are dedicated to specific FPGA technologies like high-speed interfaces and external memory. Finally, you can also view and post questions to the community forum, monitored by skilled Intel FPGA application engineers. One more thing. When you registered for this e-learning, you should have received a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey now. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this training, introducing you to the Platform Designer system design tool.